Alright, welcome. So we're going to be talking about section 14.6, which is known as directional derivatives. And this directional derivative is also going to include something that's known as the gradient. Now, in the previous sections, what we were looking at is we were looking at derivatives, and these derivatives were taking with the derivatives that we were taking were with respect to x or with respect to y. So in a general sense, they were always parallel to either the x-axis or the y-axis when we were talking about those curves being projected onto the x and y-axis. Now, in this section, we want to elaborate a little bit more. As you can see on the screen here, I have drawn a function here which represents a surface, and that's going to be in blue, this function f of x, y. And on the x and y plane, I drew a derivative on there. So this derivative on the x and y plane, I'm going to say that this vector is vector given by AB. And this vector given by AB can be thought of as any two-dimensional component vector. Because it's a two-dimensional vector, it can make, or it will make, some angle with the positive x-axis that we call theta. Now, thinking back in terms of how we want to work with these vectors, we want to make sure that we always deal with unit vectors. So not only is v going to be defined by AB, but we're going to consider v to be a unit vector. So the magnitude of vector v is going to be equal to 1. Now, if that's the case, then we're going to be able to extract a few more items from here. The items that we're going to be able to extract is that using our trigonometric components, we can rewrite vector AB in terms of cosine theta and sine theta component-wise. Typically it's r cosine theta and r sine theta, but since the radius is going to be 1 because of the unit vector length, then that naturally transcribes to cosine theta, sine theta for all of these unit vectors. So this unit vector then now allows us to express it in two different ways. One, unit vector can be based off of the angle, or two, unit vector can be based off of their individual components that land in the x and y plane. Now, this is going to be very beneficial because imagine that we can then start moving this theta, and this theta will then move the derivative along the surface. So it's going to be able to change the orientation of that derivative. In other words, it's going to give it a direction when we take that derivative, and hence the name directional derivatives. So before we go any further, I want to formally write the definition for this directional derivative that we are going to be using. All right, so it'll pop up on the screen in just a second. So here's the definition for the directional derivative. The definition states that the rate of change for the function f of xy in the direction of the unit vector, and in this case we're going to call it u for unit vector, component-wise in AB is given by the directional derivative. The notation that we use is this notation for the derivative. If you go back to section 14.3 when we were looking at partial derivatives, this is the very last notation that we used in that section. Alright, so the derivative, in this case with respect to the unit vector for the function f of xy. Limit-wise, what that looks like is using that notation for the directional derivative, that's just the limit as h is approaching 0 for the function where a and b, or sorry, x and y are allowed to change in the direction of a and b along with this given increment that we're looking at for h. Using this definition, we'll be able to get this directional derivative. Now, how does a directional derivative look like in more terms of algebra? That derivative looks like this. That if we want to take the derivative for a direction, then all we have to do is look at the partial derivatives in terms of x and in terms of y and multiply them by their direction given by a and b. Or if we don't have a direction component-wise per se, then we can automatically convert into polar coordinates or into trigonometric ratios to say that when we start looking at this directional derivative, we need a direction given by either the component vector or given by the theta that's made by that component vector. So we're going to be using these two equations here to analyze some directional derivatives. Alright, so here goes your first example. This example is going to say find the directional derivative. For part A, we're going to be looking to find the directional derivative in the direction of the unit vector and at the given point 2, 0 for the function where the function f of xy is given by x e to the power of xy plus y, and the unit vector u is the unit vector in the direction of theta, which is going to be equal to 2 pi thirds. Alright, so looking at this directional derivative now. So the directional derivative here, we're going to need some partial derivatives, so let's go through and work with those partial derivatives first. We're going to need the partial derivative with respect to x. So for the first one, we're going to need to do a product rule here, derivative of the first multiplied by the second function plus the first function multiplied by the derivative of the second function there we are, and then y is a constant there, so we don't need to worry about that. Now we need to evaluate this derivative at the ordered pair 2, 0. So the ordered pair 2, 0, let's evaluate that really quick. This is going to be e to the power of 2 times 0 plus 2 times 0 times e to the power of 2 times 0. Now, as you'll see, since this is second terms multiplying by 0, that just goes to 0, and then we just get e to the power of 2. Or sorry, e to the power of 0, which is just 1. My apologies. Next, we need the second partial derivative. So the first order partial derivative for y, this is going to be in terms of xy, is going to be x squared e to the xy plus 1. Making this evaluation at 2, 0 will now give us 4 times 1 plus 1, which gets us 5. Nice. Now all we need is the angle measurement and we'll be good to go. So the angle measurement in this particular case, if we want to find the directional derivative in the direction of the given unit vector, then all we need to do is we need to figure out what is going to be that cosine of theta. Alright, so let's go through and let's figure out what that cosine of theta is going to be. Alright, so here we go, partial of f, that's going to be 1 multiplied by cosine of 2 pi thirds plus next derivative, that was 5 multiplied by sine of 2 pi thirds. And just as if we were in class, I realized I made a mistake, so I'm going to go back and I'm going to correct that mistake. That was not the partial with respect to x. There we go. Partial with respect to x. There was a mistake right up here in the formula that I wrote. No mistake here going on. Okay, good. So all we need to do now is figure out what is cosine at 2 pi thirds. So cosine at 2 pi thirds, if you agree with me that 2 pi thirds is in the second quadrant, all we need to do is find cosine there. Cosine in the second quadrant is going to be negative. All we need is a reference angle. The reference angle is going to be pi thirds. Pi thirds can be thought of as 60 degrees. So when we look at 60 degrees, we want cosine of 60 degrees. So cosine of 60 degrees should be root 3 divided by 2, or excuse me, 1/2. So it's negative because it's in quadrant 2. So this is negative 1/2 plus 5. And sine at 2 pi thirds, well, that's just going to be the trigonometric complement for it, which means it should be root 3 over 2. Sine is positive in quadrant 2, which means at the end of the day, we get this answer to be that the directional derivative is 5 root 3 minus 1 divided by 2. Awesome. And that's all there is there. Nothing else to do. Let's look at part B. In part B, we want to find this directional derivative for this function f of x, y, z. And this is going to be where the function f of x, y, z is equal to x squared, x squared z plus y cubed z squared minus xyz, and that's going to be in the direction of vector v, which is given by -1, 0, 3. Alright, so we got some work to do here by taking some partial derivatives. And that's what we're going to do really quickly, is we're going to find these partial derivatives. So the first partial derivative, partial with respect to x. Partial derivative with respect to x, this is going to be 2xz minus yz. Partial with respect to y, for this function, that's going to be 3y squared z squared minus xz. And then the partial with respect to z for this function will be x squared plus 2y cubed z minus xy. Nice. Now, one more thing. The vector that is given to us, this vector, needs to be a unit vector. To be a unit vector. So what we're going to do is we're going to make it into a unit vector. So that means we need to find the magnitude of vector v, and we can do that by squaring each individual component and adding those results and then taking the square root of that, which means the magnitude of v should be 9 plus 1, that's going to be 10, so that's going to be square root of 10. So here goes my unit vector. Unit vector is going to be 1 over root 10 multiplied by -1, 0, 3. Nice. Alright, so now we have the unit vector, and now we have all the partial derivatives, which means we can now go ahead and we can now start writing this directional derivative. So the directional derivative for this function f of x, y, z will now be the first partial derivative with respect to x. That was 2xz minus yz excuse me, and this is going to be multiplied by the a component of the unit vector. The a component of the unit vector is -1 over root 10 plus the next partial derivative, which is 3y squared z squared minus xz, multiplied by the second component of that unit vector, plus x squared plus 2y cubed z minus xy, multiplied by the component of the last unit vector, or sorry, the last component of the unit vector, which is 3 divided by root 10. All we have to do at this point in time is go ahead and simplify. Now I'm going to go ahead and I'm going to color code these, that this first piece was this first piece and was multiplied by that first piece. The second piece, this one here, was multiplied by that one. And then the third piece here was this third piece here, and it was multiplied by that. There we are. Alright, so let's simplify. Notice that all of these values have root 10 in the denominator, so I'm going to factor out that root 10. That way it makes calculations a little bit easier. Alright, distribute the negative in here, so we're going to have yz multiplied, or sorry, yz minus 2xz. Excuse me. There we are. Second component, that's going to be 0 because it's being multiplied by 0. Third component is being multiplied by 3, so I'm going to distribute. So that's going to be plus 3x squared plus 6y squared z minus 3xy. Alright, and if we have any like terms, and we go ahead and combine any like terms, and as we're looking at this, there should be no like terms, which means this is the final answer. We got nothing else to do here. Awesome. That's it. So these are the two examples that I wanted to illustrate with this directional derivative. Now, one thing about directional derivative is that we haven't really tied in anything in chapter 14 with vectors so far. And in this section, we actually get to talk about vectors with surfaces. Now, if you recall, back in chapter 12 and chapter 13, we started developing this whole concept of vectors. And we started working with these vectors and their properties to illustrate some of these curves that were traveling through space. Then in chapter 14, we said, well, what if we don't just want to look at those curves? What if we want to look at a collection of those curves known as surfaces? And we can definitely look at those surfaces, but at the end of the day, they were, again, just a collection of curves, and these curves were denoted as vectors. So we now want to tie in these vectors with these surfaces. Now, the way we're going to make this tie-in is by using the definition that we were, let's say, working with. So, the definition for the derivative, for this directional derivative, looks like this. There we are. Alright, so now for the purposes of this example, I'm going to condense this just a little bit more. Instead of just writing out the function of x and y, I'm going to condense shorthand notation and just write this out here. Now, one of the things that we want to see here is that this directional derivative kind of looks like it's made up of addition, in other words, the sum of two products. That should remind you of some item or some topic that we discussed back in chapter 12, somewhere along chapters 12:3, which was known as the dot product. Now, could I then express this directional derivative in terms of a dot product? Wow, That's rather interesting because, again, now this is going to tie in that directional derivative is really just made up of two vectors. One being the partial derivative vector, the other one being the unit vector. And this is the key that we need, because what we're going to do is we're going to develop this notation. This notation is going to be known as the gradient. The gradient of f. The notation that we use is right above. We use this upside down triangle known as del. So we'll say del of f is equal to the vector where the components of the vector are the partial derivatives of the function that we are working with. So every function can have a gradient, and now we need to know how to find these gradients. All right. So for the next examples, we're going to work with directional derivatives again, but this time around, we're going to use our newfound gradient to elaborate on those directional derivatives. All right, so let's work with the first example then. Find each directional derivative. Part A. We're going to be looking for the directional derivative for the function f of xy, where the function is defined by x times cosine of y in the direction of v is equal to 2, 1. Alright, so directional derivative. First, let's find the gradient. The gradient of the function, that's going to be the partial derivative of x, so that's going to be cosine of y. And then the partial derivative of y, which should be negative x sine y. There we are. So we got the gradient. Now we need a unit vector. Since we're not given a unit vector, we need to find that unit vector. Take the magnitude, which will be root 5. So the unit vector is 2 over root 5 and 1 over root 5 for the components. There we are. So when we want to look at this directional vector for this function, all we have to do is take the dot product for these two. So let's take the dot product. Multiply the first two and then add. So 2 root 5 cosine y minus 1 over root 5 times x sine y. And there it is. That's your directional derivative. All done. Nice and concise. Part B. Part B, we want to find the directional derivative for the function f of x, y, z, which is given by sine of yz plus natural log of x squared. And we want this at the point 1, 1, pi. And this is going to be in the direction of v, which is 1, 1, negative 1. So again, to start off, we're going to need the gradient. So let's find the gradient first. So finding the gradient of this function, we're going to take the partial with respect to x. So the partial with respect to x here, that's going to be 1 over the argument, which is x squared. So 1 over x squared, and that's going to be multiplied by the derivative of the inside, which is 2x. So that should be... Oops. All right, my apologies. I had a package at the door, but now everything's going to be good. All right, so 2x divided by x squared, that should give us 2 over x. Now, the partial derivative for sine of yz with respect to y, that should get us z multiplied by sine of yz. Then the partial derivative of the function with respect to z should get us y times sine of yz. Now, excuse me here because I said sine, and you are absolutely correct. It is not sine. The derivative is cosine. My apologies. Cosine and cosine. There we are. Perfect. So now that we have this, then we need to find that unit vector. So the unit vector, let's go ahead and let's calculate that unit vector. Let's see, we have 1, 1, negative 1. So that's going to be root 3. So that unit vector is just 1 over root 3, 1 over root 3, and then negative 1 over root 3. Nice. All we need to do for this directional derivative is evaluate this directional derivative at the point 1, 1 pi. Oops, excuse me there. 1, 1 pi, which means we got to take the directional derivative evaluated at 1, 1 pi, and we need to take the dot product with that directional derivative and the unit vector. Alright, so let's go through it. Directional derivative at 1, 1 pi. In other words, the gradient at 1, 1 pi. That's going to be 2. Let's see, cosine. That's going to be y is 1, and then that's pi. So cosine at pi, that should be negative 1. So that's going to be negative pi. Cosine yz, again cosine at pi, that's going to be negative 1. So negative 1 times 1 in this case, that's going to be negative 1. And we're going to take the dot product with 1 over root 3, comma, 1 over root 3, and finally negative 1 over root 3. Alright, notice that there's a root 3 in all of the denominators here, so what I'm going to do is I'm going to factor that out, and I'm only going to work with the numerators. So the numerators here, that's going to be 2 times 1 plus negative pi plus negative, or positive 1 actually, plus 1. There we are. Which means we get a final result of 3 minus pi divided by root 3. There we are. That's your final answer. So we got the directional derivative using this whole concept of a gradient. Now what we want to do is we want to elaborate just a little bit more. Alright, so I'm going to write on here this theorem that we have that says that the maximum value of the directional derivative for some function is given by the magnitude of the gradient. Remember, the gradient was a vector, so if we take the magnitude of that gradient, it will be the maximum value for that directional derivative. Now, what direction does this occur in? In other words, we want at one specific point on this surface to figure out what direction we need to go to either increase the fastest or decrease the fastest, and will occur in the direction given by the magnitude, or sorry, given by the gradient of f. So the gradient, not only does it tell us what direction we're taking this vector in, it also tells us the direction at which the rate will increase the fastest or decrease the fastest. That is super helpful. And for homework, you are going to have a couple of assignments to work through on how to find that maximum value and what direction it's going to be traveling in. All right, so that now wraps it up for section 14.6, which was these directional derivatives and the gradient vectors. Now, next time we're going to cover section 14.7, and 14.8. Those sections are a little bit long, but I think we can get through them all in one class period. All right, so after we're done with section 14.7 and 14.8, then we'll go ahead and we'll talk about scheduling exam number 2 for you all. All right, or sorry, exam number 3 for you all. All right, so that's it for today. I'll see you all next time.